Hello everyone, in this video we're going to learn how to verify some basic trigonometric identities. We'll go over 3 techniques for accomplishing such a task, and before we do so we're going to brush up on some of our algebraic skills, starting with what is known as complex fractions. Oftentimes we have occasion in a trigonometric class to deal with expressions like these two, and they're basically of the algebraic form a over b over c over d. So we have one fraction over another fraction, and this technique we're about to discuss, this shortcut, will only work when you do have only one fraction over one fraction. If you have more than one term either on the top or on the bottom, this won't work. But most of the fractions that are of a complex nature that we'll encounter will be of this form, so this will be useful for us anyway. So basically we know that this means a over b divided by c over d, which means a over b times the reciprocal of c over d, which is d over c. So we end up with AD over BC. Now when we look at the original complex fraction, we realize that means we get the outer product here over this inner product. So that's going to be the shortcut we're going to remember and use. So whenever we see a complex fraction of the form a over b over c over d, we'll realize that we can just take that outer product, that's going to be our numerator, and this inner product is going to be our denominator. So for example, applying it to this first expression here, we get 1 times sine x, which is sine x, over cosine x times 1, which is just cosine x, and as we know, that is simply tangent x. Or we can apply it to a slightly more complex situation like this, and notice we do have 2 terms here, but we still only have one fraction line, so this is considered a fraction of the form a over b over c over d, so we can go ahead and apply the shortcut. So we're going to get this outer product over this inner product. So we end up with 1 minus cosine squared x over 1 minus sine squared x. Now we remember that sine squared x plus cosine squared x equals 1 from our previous video. So notice that if I move cosine squared to the other side, I end up with sine squared x equals 1 minus cosine squared x. Or if I keep the cosine squared on this side and move the sine squared to the other side, meaning subtract sine squared from both sides, I end up with cosine squared x equals 1 minus sine squared x. So I can replace this 1 minus cosine squared x here with sine squared x. We can also replace this 1 minus sine squared x with cosine squared x. And as we know, that's just going to be the square of the tangent, so we get tan squared x. So these are just some of the quick things we can do by using this nice shortcut from algebra. The next kind of algebraic review is going to be regarding expressions that are squares of binomials. So the general form for that, we have f plus l squared, which, if you recall from the algebra class you had, that's going to be f squared plus 2fl plus l squared. So that can easily be done on a table as well. See, we can put f plus l, f plus l, and multiply it out, and we get f squared plus fl plus fl plus l squared. And of course, these two FLs can be combined, and that's where we get f squared plus 2FL plus L squared. Or we could just multiply it out by foiling. So the other one that we knew was for the square of a difference. The first one was the square of a sum, and the formula is very similar. It's just that we get f squared minus 2FL plus L squared. So the only difference is that the middle term here becomes negative. All right, so let's go ahead and apply it on the right here. So we end up with, notice we get the first one squared, so the square of the sine, and as you know, we write it in this way. We never put the square on the alpha, we always put it right above the n. So we get sine squared alpha minus 2 times the first times the second, so we get 2 sine alpha cosine alpha plus the second one squared, which is just going to be cosine squared alpha. Now if you notice, there's a familiar expression here. We have sine squared alpha plus cosine squared alpha, which of course we remember is just 1. So we can actually write this as 1 minus 2 sine alpha cosine alpha. We're not in the business of verifying identities at this moment. We're just doing some algebra review. So for the next one, notice here we can consider, for this expression, right, we can consider our f to be 1 and our L to be tangent of theta. So we're going to get f squared, which is just going to be 1 plus 2 times f times L, so that's just going to be 2 tangent of theta plus L squared, which is going to be tangent squared of theta minus 2 tangent of theta. And of course we realize that here this term is going to cancel out with that term, so we end up with 1 plus tangent squared theta. Just to brush up a little bit on that rule. All right, and then the next kind of situation we encounter quite often, actually probably more than any other, is the difference of squares situation. So if you recall from algebra, the formula for that was f squared minus L squared equals f plus L times f minus L. Sometimes people prefer to put the f minus L first and then the f plus L, and it makes no difference, as you know, because of commutativity of multiplication. So just an algebraic example, like if we had x squared minus 81, we know that this is basically x squared minus 9 squared. So here f is x and L is 9, so we can easily factor that as x plus 9 times x minus 9. Okay, so we can do exactly the same kind of thing with trigonometric expressions like this. Here we do have a difference of squares. Sine squared theta is obviously a perfect square, and 1 is a perfect any power you want it to be, so it's a perfect square as well. So basically we're going to realize that f here is sine theta and L here is 1, so we're going to apply this formula to that f and that L. So we're just going to end up with f plus L, which is sine theta plus 1 times quantity sine theta minus 1. And we can also apply it to a more complex situation like this. Notice that those are perfect squares. The item that needs to be squared, or the expression that needs to be squared to give us sine to the fourth theta, is sine squared theta. So in this first round of factoring, f equals sine squared theta, and what needs to get squared to give us cosine to the fourth theta is cosine squared theta. So now we go ahead and factor using the formula. So we end up with sine squared theta plus cosine squared theta times sine squared theta minus cosine squared theta. And of course, we know that the first quantity here is just going to be 1. So we just get 1 times that expression. So we're just going to get this expression. Again, remember, this is 1. So now we end up with sine squared theta minus cosine squared theta. So it's all very simple. Just make sure you're understanding it and you're following along. The best way is to make sure that you write down these problems along with me and work them out. Make sure you can do them on your own before you move forward. Remember, math is not a spectator sport. You don't sit there and watch it like a movie. You have to participate. That's the only way to really learn mathematics effectively. Next, we'd like to look at factoring trinomials of the form ax squared plus bx plus c, and in pure algebraic term those are called quadratic trinomials, and here we're actually going to be more interested in the quadratic form. So in other words, we want to look for a square term and then a first degree term, and the square term is going to be the square of that first degree variable part, as we have here as well. See, when you square cosine squared, you get cosine to the fourth, and then at the end we'll have a constant. So just to look at a purely algebraic example, consider 2y squared plus 3y plus 1. As you know, we usually just factor these by trial and error, even though there's the grouping method as well, but we always go to this method first. It's much quicker. If it works, we just go with that method. So we want two expressions in the first spots that give us 2y squared. So we know that's going to be 2y and y. And here in the second spots, we want two expressions whose product is 1. So those are going to be simple, just 1 and 1. These are all positive, but nevertheless, you always want to make sure that this inner product, which is y, and the outer product, which is 2y, add up to the middle term, which is positive 3y. And that's why I usually don't put the signs till I realize what they need to be. And in this case, it's simple. Since they're all positive, obviously to get 3y out of y and 2y, they'll both need to be positive as well. So we'll have plus and plus. Now, notice how similar these two look. That's because I did that on purpose. Notice the only difference is instead of y, we have sine x as the variable. So we'll go ahead and factor it in exactly the same way. We'll open two sets of parentheses. And in these two first spots, we're going to want two expressions whose product is 2 sine squared x. So we'll use 2 sine x instead of the 2y here, and sine x. And of course, for the 1, we're going to use plus 1 and plus 1. So just like that. Very simple. This is also quadratic in form. So sometimes people prefer to use substitutions, or you can just do it directly. I prefer the direct approach, but I'll show you both. So notice that here we want two expressions in the first spots whose product is cosine to the fourth x. So of course we can use cosine squared x and cosine squared x. And in the second spot, we're going to use just 1. And we notice that this is actually a perfect square trinomial. So you may have recognized that from the beginning, or if you didn't, you see it now. So we can always write it in that form. Now the substitution method works like this. So you let u, for example, equal to cosine squared x. So that is going to imply that u squared equals cosine to the fourth of x. So we can rewrite the expression now as, instead of cosine to the fourth x, we can put u squared plus, instead of 2 cosine squared x, we can put 2u, because cosine squared x is u. So plus 2u plus 1. So you get this simpler looking expression, and you go ahead and factor it as u plus 1 times u plus 1, which is u plus 1 squared. After u has served its purpose, you go ahead and substitute back what it was, which was cosine squared x. Cosine squared x plus 1 squared. So either way is fine. As you can see, the direct method works just fine. So if you're comfortable enough with that, you don't have to go through all this. But knowing and understanding the substitution method is going to be useful in calculus and more advanced courses. So that's why I wanted to go over it anyway. So make sure you understand this before we proceed. The next type of factoring we want to review has to do with the sums and differences of cubes. And if you recall from algebra, these are the formulas that we utilize to accomplish this kind of factorization. So for the sum of cubes, we know that when you have a first expression cubed plus a second expression cubed, that could be just a simple variable, or it could be an entire expression, makes no difference. The way it factors is you go f plus l, quantity f plus l times quantity f squared minus fl plus l squared, and there is the formula for the difference of cubes. You can see they're very similar. You just have to remember that the signs work out in a different way. In the plus case, notice the signs alternate, positive, negative, positive. The signs you can see, of course, there's a sign on this term as well, which we don't really talk about, and this one, but the ones you can see, they alternate, positive, negative, positive. For this one, the first group has a negative sign in it. It's a difference, but in the second group, it's all sums, so only plus signs. So here in this case, we're going to recognize the fact that first of all, we're using this top scenario, and we have the sum of 2 cubes. Now we need to determine what f is and what l is in order to get these done properly. We can see here f is sine alpha and l is cosine alpha. Now you know that when you write sine cube alpha like this is actually sine of alpha cube, like that, quantity sine of alpha cube. Now the reason we put this 3 where we put it is because if we put it over here, it could be misinterpreted as alpha getting cubed first and then applying the sign. So that's why we put the 3 right above the n, and that gets rid of that ambiguity. So now we're going to go ahead and factor it using this top formula. So we get f plus L, so we're going to have sine alpha plus cosine alpha, because that's what f and L are, and then times f squared. So now we're going to square f, which is sine alpha, so we get sine squared alpha, minus, now we're going to multiply those two, so we get sine alpha cosine alpha, and then plus L squared, so plus cosine squared alpha. All right, so of course, if there is any simplification that we can see possible, just as was the case in an algebra class, we take care of it. But in this case, we're mostly going to be looking for trigonometric types of simplification. And indeed, we notice here that we have a sine squared plus a cosine squared. Now we know that that's a Pythagorean identity, and that's just 1. So we can rewrite the problem, the factorization that is, now as quantity sine alpha plus cosine alpha times quantity. Instead of the sine squared plus cosine squared, we'll put 1. So we get 1 minus sine alpha cosine alpha. And there we have factored sine cube alpha plus cosine cubed alpha. So that's how you would handle a sum, or in fact a difference of cubes. You would just be careful about using the correct signs depending on which one of these two scenarios you're dealing with. Make sure that you can handle that on your own, and then we'll proceed. That brings us to the end of our review of factoring techniques, and now we're going to utilize some of what we have learned to actually go ahead and move on to the business of verifying trigonometric identities, which is basically a type of a proof that we're going to be learning about, and which is one of the most important things that we're going to do in this trigonometry class. So let's go ahead and look at how we can tackle that task. Okay, as far as verifying identities are concerned, the first technique we're going to discuss is starting with one side and working our way to the other side. So basically, you write one of the sides without changing it at all in any way, and then through some legal steps, you try to work your way to the other side. You can start with either side and work your way to the other side. For example, in a problem like this, there's not a whole lot we can do with 1. So we'll go ahead and start with the left side and see if we can work our way to the right side, which is 1. So again, this is a form of proof, so you can always start it with proof. So we start with cosine squared theta times tan squared theta plus 1, and one of our standard techniques, which is we discussed in the last videos, is to convert everything that is not already a sine or cosine into the terms of sines and cosines if possible. And of course we can do that here because we can write tangent as sine squared theta over cosine squared theta plus 1. So now we're going to go ahead and distribute the cosine squared theta into the group here. So we end up with cosine squared theta times sine squared theta over cosine squared theta plus cosine squared theta times 1, which is just cosine squared theta. And of course, we can see here that we have some cancellation possible. So we end up with sine squared theta plus cosine squared theta, which of course, as we know from previous discussions, that equals to 1. And we just verified the identity that we were supposed to verify. So at this point, we can say QED. That stands for Quod Erat Demonstrandum, which basically just means the proof is finished. So it's very important that you realize for this to be presented in the proper manner, you need to start with one side without changing it in any way. And then through some legal steps, try to work your way to the other side. And this by far is the most popular and applicable technique among all the techniques that we're going to discuss today. So most of the problems you'll encounter, you'll be using this approach. Start with one side, work your way to the other side. Make sure you can do that on your own, and then we'll look at another problem. Now we'll try to verify this identity, and usually with trig identities, it's easier to get from a sum to a product. So we'll go ahead and start with the left side. So we have cotangent theta plus tangent theta. Notice I started by writing that without any modification whatsoever, because the point is for me to show that I can get from that to this other side, and that's why I don't change the left side at all. Okay, so now we realize that we can write cotangent of theta as cosine theta over sine theta, and we can write tangent of theta as sine theta over cosine theta. Now we're going to do some algebra here and find the common denominator, which is not that hard. Sine theta, cosine theta. So in order to get to this common denominator, this sine theta needs to be multiplied by cosine theta. I'm bringing a different color to make it. And we're going to do the same on the top. And in order to make this cosine theta become this, the common denominator, we're going to have to multiply by sine theta. So of course we'll have to do the same on the top. All right, so now we notice that our new numerators are cosine squared theta plus sine squared theta. The expression on the top should look familiar to you by now. As you know, that's just 1. So we get 1 over sine theta cosine theta. So as we do this, we keep our eyes on the target, which is secant theta cosecant theta. For the first time, it looks like we're getting close because we've taken a sum and we've turned it into an entire product. So at this point, all we're going to do is we're going to split those. We can always write that as 1 over cosine theta times 1 over sine theta. Notice these two expressions are the same. And the only reason I put 1 over cosine theta first is because I want to end up with secant theta in the first spot. So I get secant theta, and we know that 1 over sine theta is cosecant theta. And at this point, we're finished. So we verified the identity, and we can call it done. So try to work this out without looking at all before you join me for the next problem. Okay, next let's try to prove this identity. And in most trigonometric identities, it's usually easier to go from a sum to a product. So we'll go ahead and start with the left side So we'll go ahead and write the left side exactly as it is. Cotangent theta plus tangent of theta. Now we'll use our standard technique of just converting all expressions to sines and cosines if they aren't already in that form. So we can write cotangent of theta as cosine theta over sine theta, and we know we can write the tangent of theta as sine theta over cosine theta. So now we're going to go ahead and combine those using our algebraic skills, which is going to require a common denominator, which is sine theta cosine theta. And of course, for this first denominator to become the common denominator, we're going to have to multiply it by cosine theta, which means we have to do the same on the top. And for the second denominator to become the common denominator, we're going to have to multiply by sine theta, which means we have to do the same on the top. So now we're going to combine our new numerators, which are cosine squared theta plus sine squared theta. So this expression should look familiar to you, as you know by the Pythagorean identity, that is 1 over sine theta cosine theta. Throughout this, we keep an eye on the target, and now we realize for the first time we've gone away from the sum form, and we can now write this as a product. So if I just break that up, I notice I want secant first and then cosecant, so I'm going to write 1 over cosine theta first and multiply that by 1 over sine theta. Notice that this is just a rewrite of the previous line, and they have the exact same expression in them. So basically we know 1 over cosine theta is secant theta, and we also know that 1 over sine theta is cosecant theta. And we are basically done. We started with the left side, and through some legal maneuvers we ended up with the right side, so we are finished. So make sure you can do that on your own before you continue. Okay, in this next problem we're going to explore our second technique, which is basically showing that both sides are equal to the same expression. So sometimes working with one side and trying to get to the other side doesn't yield much fruit, as we'll see in a minute. In those cases, we can try our second technique in the following way. So we will start working with the left side of the expression, which is, so we can say the left-hand side. This is still going to be considered a proof, it's just a different technique. So we say the left-hand side equals cosine alpha over secant alpha plus sine alpha over cosecant alpha, which we can go ahead and write that as cosine of alpha over 1 over cosine of alpha, because that's what secant is, plus sine of alpha over 1 over sine alpha, which is what cosecant is. I wrote these extra ones because I wanted you to realize we're in the a over b over c over d form, so we can do our outer product over near product trick to get cosine squared alpha plus sine squared alpha. And of course we know that this is 1. You can see why we're trying a different technique, because if we had tried just to start from the left side and end up with the right side, we would have gotten here and we would go, okay, now what, right? So in these cases, and they're not that common, but this technique works well. So now we'll start working on the right hand side of the equation, or the identity, which is a special equation which is always true. So we get right hand side equals secant squared of alpha minus tangent squared of alpha. Now if you paid attention in our last video when we discussed the trigonometric identities, which I will remind you here, were these three identities: sine squared alpha plus cosine squared alpha equals 1, the most important one. Now dividing both sides of that first identity by cosine squared gives us tangent squared alpha plus 1 equals secant squared alpha. Or if we take the first identity here again and divide both sides by sine squared instead of cosine squared, we get 1 plus cosecant squared alpha equals 1 over sine squared, which is actually backspace there for a minute. We need to undo that. Cosine squared over sine squared is cotangent squared alpha equals 1 over sine squared alpha, which is cosecant squared alpha. So we also said that we need to know all the related equations. Now, particularly we're interested in this middle one. Notice that if we take tan squared to the left side, to the right side, we get 1 equals secant squared of alpha minus tangent squared of alpha. So by the way, none of this is all side work. None of this is part of our proof. I'm just reminding you of these three versions of the Pythagorean identities. And so we realize right away we can go ahead and say this is equal to 1. So notice we just showed that the left hand side and the right hand side are both equal to 1. So therefore the left hand side equals the right hand side. Notice we can say that instead of having to rewrite all of that, and we're basically done. QED. We just proved the identity. So in this technique, you work on both sides of the identity and show that they both end up being equal to the same expression. And that's another way of verifying trigonometric identities. Okay, let's go ahead and do one more problem using this technique that we just learned, working from both sides, and then we'll go back to technique 1. So let's go ahead and start working on the left side. Before we do, however, we kind of scope the both sides of this identity and realize it's rather cosine heavy, right? So the thinking process that I'm going through is let me see if I can somehow get both of these equations in terms of cosine alone and see if that gets me anywhere. So let's go ahead and try that. So we're going to call the left hand side LHS, and we'll just write down what it is. It's cosine theta plus 1 over tangent squared theta. So I know that I can, for example, go ahead and replace tangent squared theta with either sine squared theta over cosine squared theta, or better yet, since I'm thinking to myself that I want to get only in terms of cosine, I remember from the problem we just did, in fact, that I can replace tan squared theta with secant squared theta minus 1. Remember, again, this is side work here. Remember that we had sine squared theta plus cosine squared theta equals 1. From that we got tan squared theta plus 1 equals secant squared theta. So if I solve this for tan squared, I get tan squared theta equals secant squared theta minus 1. So I'm going to go ahead and replace tangent squared theta with secant squared theta minus 1. By the way, these derivations are not unique. You may take a different approach and be able to prove it in a different way, and they're both valid. Just so that you know, there's not only one way of doing these verifications. So now, in fact, I encourage you to try different approaches. That's the only way you're going to become real master of these types of proofs. So now we go ahead and again, remember the goal is to see if we can get everything in terms of cosines. So I'm going to replace secant squared with 1 over cosine squared theta minus 1. Now I realize that I can go ahead and write the top as cosine theta plus 1. Let me go ahead and throw a 1 under that so I can create a complex fraction. Downstairs I have that subtraction, which I'm going to find the common denominator for, which is cosine squared theta, and this denominator is already cosine squared theta. The other one needs to be multiplied by cosine squared theta, which means the 1 on the top also needs to be multiplied by cosine squared theta. So once we do that, we end up with 1 minus cosine squared theta. So now we can do our outer over inner trick to get cosine squared theta times cosine theta plus 1 over 1 minus cosine squared theta. We pretty much do have an expression in terms of only cosines. However, I notice an expression here that I should recognize. That's a difference of squares. So if we go ahead and factor that, we end up with cosine squared theta times cosine theta plus 1 over notice that f is 1, L is cosine theta, and we're using the f squared minus L squared equals f plus L times f minus L factoring formula. So we end up with 1 plus cosine theta times 1 minus cosine theta, and of course 1 plus cosine theta and cosine theta plus 1 are the same by additive commutativity, so we can go ahead and cancel those, and we end up finally with cosine squared theta over 1 minus cosine theta. Now you can see why your algebra instructors told you, hey, you really need to know this. You're going to need it in your future classes. Because what we're basically doing here is mostly algebra. It has very little to do with classic trig, as you've seen us do for the first part of the term. So, it looks like a pretty good spot to stop and start working on the other side now, see if we can get something in terms of only cosines as well. So now we'll go ahead and call the right hand side cosine theta over secant of theta minus 1. I'm just writing the right hand side without changing it. So I notice that I can replace that secant of theta downstairs with 1 over cosine theta minus 1. Let me go ahead and throw a 1 under that. Now in my next step, I'll go ahead and throw a 1 under the cosine theta on the top too, so I can get my a over b over c over d form in a minute. So I notice that cosine theta is the common denominator for these two fractions, and this is already cosine theta, no change needed here, but this one needs to be multiplied by cosine theta. So we do that, and we do the same on the top. So now we notice that we end up with cosine, let me create a little bit of space here. The cosine theta is the common denominator, so on the top we get 1 minus cosine theta. Okay, so now we have the complex fraction. We can do outer over inner, and we end up with cosine squared theta over 1 minus cosine theta, which is great news because that's exactly what we had managed through much manipulation to get our left-hand side to look like once we put it in terms of cosines only. And now that we have shown that the two sides are equal, we can say therefore the left-hand side equals the right-hand side, and that means we are finished. QED. Okay, so that's a pretty decent problem. It has a nice level of complexity. I recommend you rewrite it and see if you can crank it out on your own without any help from what we've done here. And that'll be a great way to verify your understanding before you proceed. Okay, let's go ahead and take a look at this identity, which we'll use a technique 1 for again. And it's going to have an interesting point about it, which we'll explore. So let's go ahead and try to go from left to right since we're using technique 1. Remember, we start with one side and try to work our way to the other side. So we start with cotangent of alpha plus 1 over cotangent of alpha minus 1. And we go ahead and notice the fact that the signs here are similar. So as much as possible, we'd like to keep the general structure of this the same, since that's already in the right place as far as the signs are concerned. So I'm just going to go ahead and replace the cotangent with cosine alpha over sine alpha plus 1. And down below, we'll go ahead and do the same. So we get cosine alpha over sine alpha minus 1. I noticed that we have a complex fraction, but it's not of the type which is just one fraction over one fraction. And the way we simplify those is we go ahead and find the total LCD for all fractions in the problem, and in this case it's just going to be sine alpha. So we'll go ahead and multiply sine alpha on the top as well as the bottom of this main fraction. So we're going to end up with something like this. We're going to multiply by sine alpha, and of course we're going to distribute. So the best thing to do is just go ahead and, because of that distribution, multiply each term by sine alpha. So, and we're going to do the same down here. So again, because of distribution, we're going to get each of those terms multiplied by sine alpha. So when we clean that up, we notice that these will cancel out. So we get cosine alpha plus 1 sine alpha, which we can just write as sine alpha, over here. Again, these signs will cancel out, so we get cosine alpha minus sine alpha. So the point that I said, which is a little bit interesting about this problem, is the fact that we're going to have to bring something out of the blue sky to handle this problem. And that has to do with the fact that we can always not only multiply the top and bottom of a fraction by the same expression, we can also divide it. And we notice here that we want to end up with tangent in our final expression, and I have a sign in both of these locations, and I know that if I divide that sign by a cosine, I'll be able to get the tangent that I want, and dividing by cosine will also get me the one that I want. So that's the trick that we're going to use. So we'll go ahead and divide both the numerator and denominator of this fraction by cosine theta. So we'll end up with, give us more space, so we'll end up with cosine alpha plus sine alpha over cosine alpha over cosine alpha minus sine alpha over cosine alpha. So of course we can split those up, so we end up with cosine alpha over cosine alpha plus sine alpha over cosine alpha for the top, and downstairs we have cosine alpha over cosine alpha minus sine alpha over cosine alpha. And of course now we have 1 plus cosine alpha over cosine alpha is 1, and that's tangent of alpha. And downstairs we have 1 minus tan alpha, and that's basically what we were supposed to prove. So QED. Now, this is a problem that you can also work from the right to the left hand side, and I encourage you to try that and see if you can get that. That will be excellent practice before you proceed. Notice that I started with the left hand side and I ended up with the right hand side. What I would like you to do is start with the right hand side, see if you can work your way to the left hand side, and you should be able to do that. And again, that will demonstrate the fact that I mentioned in the last problem, that these derivations and verifications are not unique. So make sure you do that before we proceed. Okay, now I want us to look at a problem which involves higher powers. We looked at factoring differences of squares like this earlier in the video, so you can go back to that in case you need to. In this problem, the right side is extremely simple looking, so doesn't do much good to start with the right hand side. We're going to go ahead and start with the left hand side, and of course we'll reproduce it here without any change. Sine to the 4 of alpha minus cosine to the 4 of alpha over sine squared alpha minus cosine squared alpha. Now we know how to factor the difference of squares on the top, so that should be sine squared alpha plus cosine squared alpha times sine squared alpha minus cosine squared alpha. Again, f squared minus l squared equals f plus l times f minus l. Here f was sine squared alpha and l was cosine squared alpha. And then over sine squared alpha minus cosine squared alpha. And of course, you can now see these two expressions are going to cancel out. So we end up with sine squared alpha plus cosine squared alpha, which I'm sure by now you recognize as 1. And that's it. So even though it looked a little scary with those fourth powers, etc., it was a paper tiger, right? Not too scary at all. So that's that. We'll look at one more problem with technique 1 before we move to our next technique. All right, so let's go ahead and look at this last problem that we're going to prove using technique 1. It definitely looks like there's more we can do with the left side, so we'll go ahead and start with that. We'll reproduce it without change. 1 plus cosine x over 1 minus cosine x. I always encourage you to try these on your own before you watching the rest of the video, because that's going to bring you maximum benefit. Over 1 plus cosine x. Okay, so we have two fractions here, so the only thing that comes to my mind is, why don't I try to go ahead and combine those and see what happens. So that's what we'll go ahead and try to do. So we see that the common denominator is going to be 1 minus cosine x times 1 plus cosine x. Now, this fraction here is going to need a 1 plus cosine x on the bottom, which is going to require the same thing on the top. So we get something like, we're going to multiply that. We're going to multiply this expression by 1 plus cosine x. And we're going to do the same on the top. And this next fraction is going to require a 1 minus cosine x. So we'll go ahead and multiply that by 1 minus cosine x in order to make it like the common denominator. And of course, we'll have to do the same on the top. All right, so after we do that, we end up with the new numerator here being 1 plus cosine x squared minus, and here we'll get 1 minus cosine x squared. All right, so we're going to have to remember our square of a sum, or actually a difference formula, which was, if you recall, f squared minus 2fl plus l squared. Here we need both, actually. We need the difference and the sum. So f plus l squared formula was almost the same, but the signs are different. F squared plus 2fl plus l squared. So we'll apply the square of a sum formula to this one and the square of a difference formula to the second expression. So we end up with 1 plus 2 cosine x plus cosine squared x minus, and be very careful to open parentheses here, because this minus that we just wrote down needs to get distributed. So we get minus 1 minus 2 cosine x plus cosine squared x all over quantity 1 minus cosine x times quantity 1 plus cosine x. And we're going to clean up on the top now. So we have 1 plus 2 cosine x plus cosine squared x minus 1 plus Let me go ahead and erase this now that we're done with it. And we get plus 2 cosine x minus cosine squared x all over the same denominator, 1 minus cosine x times 1 plus cosine x. Okay, so now we notice there's quite a bit of cancellation here. The 1 and the minus 1, the cosine squared x and the minus cosine squared x. So we're left with 4 cosine x. And I notice here I have a product of two conjugates. Remember the rule that had that? F squared minus L squared equals F plus L times F minus L. This time we're going to apply that formula from right to left. We say that a difference of squares yields a product of two conjugates. These two expressions that have the form of a sum times the difference of the same two terms are called conjugates. So when we use this rule and apply it to this product of conjugates, we end up with 1 minus cosine squared x. And of course, from our very first Pythagorean identity, sine squared x plus cosine squared x equals 1, we know that sine squared x equals 1 minus cosine squared x. So we can go ahead and replace the 1 minus cosine squared x with one term, namely sine squared x. And why do we want to do that? Because we notice where we're headed, and there better be only one term where we're headed. So as long as we have a plus or minus, we're not going to get there. So the first opportunity we get to get rid of that and make it one term, we're going to do that. So we get 4 cosine x over sine squared x. Let's go back to see where we want to get, and notice we're really close to where we want to be. So we need to get a cotangent, which we have one. Cosine x over one of those factors of sine x is going to give us the cotangent. And then we need a cosecant, where we're going to have a sine x left when we do that. So we should be fine. So we're just going to break this up. We're going to write it as 4 cosine x over sine x times 1 over sine x. Verify for yourself that these are the same thing, and notice we get 4 cotangent x cosecant x, which is exactly what we were trying to verify. And we are basically done. So that should be plenty of examples to get you into the right state of mind so you can handle these by now, and make sure that this was a very good heavy algebra based example. Make sure you can handle that on your own. Write it down, don't look, see if you can do it, and then come back to join me for the next technique. So the last technique we want to discuss with respect to verifying identities is the graphic technique. And from the standpoint of pure mathematics, we don't consider it to be the soundest method, because when we want to prove a mathematical statement, we want to show it for all possible values of the input, for example, in this case. And since a graph by nature is limited, we don't consider it to be the most rigorous approach, but it is a great way to get an intuitive feel for these proofs and to literally see them in action. So the way that we approach the graphic method of proving is we go ahead and give each of these expressions in the identity, on the two sides of the identity, a name. So we can call this one f of x, and we can call this one g of x. Then what we'll do is we'll go ahead and graph both of those functions and see if they coincide, because if they do, we've verified that those two identities are representing the same function. So to accomplish that, we'll go ahead and utilize Desmos here. So I'll go ahead and type in the first expression, f of x equals I'm going to use parentheses to get the fraction, so 2 plus 5 cosine x over sine x. Now notice it's still not a very dramatic graph, but once I go ahead and, in fact, that's just a cosine curve. The reason it looks jagged like that is because it's so zoomed out. But as soon as I throw in the sine x on the bottom, you know problems are going to come in, because every place where sine x is 0, which is basically multiples of pi, all integral multiples of pi, this graph is going to become asymptotic. So it's not surprising that it looks so wild, but that's not the point of what we're doing right now. So let's go ahead and put in the next expression, g of x equals 2 cosecant x plus 5. Actually, you're gonna have to use parentheses around that x, because otherwise whatever I type after the x, the plus 5, etc., it's going to consider to be the argument of cosecant. So it's one of these things with these graphing calculators you have to be careful about. So we go plus 5 cotangent of x, and let me turn that off. Notice the first graph was right there in purple. Now here's the second graph. Notice how they do in fact coincide. So that's just a quick graphic verification of this fact. Again, this is not the method of choice, and what you'll want to focus on is techniques 1 and 2, but this I felt like was a really nice presentation of these proofs, so it was nice for us to see how it works out. And we'll look at one other case with the graphic method, which is a better usage of the graphic method. Okay, so in this last example, we are going to be asking the question. We're not claiming that this is an identity, we're asking whether it's an identity or not. And if we go ahead and graph the left side of this expression, we get f of x or y, doesn't matter which one you use, equals 1 over 1 plus sine x plus 1 over 1 minus sine x. So we get that graph. Now on the next one, we're going to graph the right side of the proposed identity. We're not sure if it is. So we get g of x equals secant squared x. Okay, now this time we notice that the graphs did not overlap. So while we don't consider the graphing method to be a very sound method for proving that an identity is true, it is a perfectly sound method for proving that it is not true, because while we have very tough standards for the truth of a statement in mathematics, meaning you have to visually demonstrate that it's true for all x, which is impossible to do because of limitations of the graphing technique. It's only going to show you so many possible values. You don't have infinite time to demonstrate it for all values. All we need to prove the falseness of a statement is one place where the two functions don't agree. And of course, right here we see plenty of x values for which the values of these two functions disagree. So while the graphic method should not be used really for verifying identities, it is a pretty good method for showing that a certain trigonometric statement is not an identity. And that pretty much wraps it up for us for today. So make sure that you practice techniques 1 and 2 in particular heavily, especially technique 1, as that is the most common method used. And that should do it for us for today. Be safe till the next time we meet.